a model is what I have right here. And I made a video about this maybe about 10 days ago. I'll go back and we can look at that model. But at that time I had two species growing in here. This one is the red bean. Its biological name is Phaseolus vulgaris. And then somewhere hidden inside of here I have some mung beans growing up. Let me see if I can find one in here and pluck it out of here. Right? They're not doing so good. How can I say they're not doing so good? Is because around the same time, this is, I don't know who this belongs to, but another group left no cover on their closed system, on their jar, so they had an open system. But it allowed us to see, suppose Vigna radiata was growing in a place all by itself, and it didn't have any competition. This is how it would have done. It would have grown up nice and straight like this, but because it's in what we call a struggle for existence. Charles Darwin used this phrase, the struggle for existence, when he laid out his theory of evolution by natural selection, something that we have to study in this course. And this is Vigna radiata here if it's under competition with the red bean, Phaseolus vulgaris. Vigna radiata is the mung bean. And this is how the mung bean is doing without competition. So once there's competition, sometimes one species kind of gets subdued and it's not able to flourish and to show itself. And maybe this can apply also in human societies sometimes. If you are in a place that's too competitive, you might not flourish. And that's deep. I want to tell you guys why it's deep. It's because you guys are looking to apply to various universities, okay? Some people only have IVs and big places with big names on their list. But here's the thing. If you go to a place where everybody is way up there and you are down here like the little mung bean, you'll be struggling. And you go not to a bad place, but to a place that's the right fit for you, you could become like this. And you would flourish and grow. Eventually, everything will reach its full maturity and it will bear fruit. It will flower and bear fruit. Now, that sounds nice, but it's happening literally right here. If we look into our red bean here, our Phaseolus vulgaris, we will see these are flowers. From flowers, we will get fruit. I'll have to look up and see how I should leave this over our break and see how it will grow. But this species is winning the struggle for existence. But it too will not be able to survive here forever. Because you see, this little box with soil, it's a system. What type of system? It's an open system. And it has inputs of light, and I'm giving it water, and it's taking up nutrients from the soil. But it can only support so much. And the amount that it can support is called the carrying capacity. Photosynthesis is happening, light is falling upon this. There is a flow of light, there's a flow of water. There are transfers and transformations as the sugar is transformed into energy for growth, and starches are built, and cellulose is built, and the plant grows. Leaves would fall down, things would die, and decomposers have to come into action. We have living components in here called biotic factors, non-living components in here called abiotic factors. You see, all of these words that I'm using, you guys have to be able to use them in the right context. So in ESS, it's not about just memorizing what is this, what is that, what is that. It's about putting it into the big picture and relating it to a model like this one here, or relating it to a real system. We all built our closed systems, which I have mine here. And yeah, it's looking full of mold and fungus right now. But that is very, very essential. Because what that's going to do in time, I'm going to leave this right here in this room over the break, and we'll have it like this closed until next year. I'm guessing eventually the green and all of these leaves will disappear. This will totally disappear in here. As I put the seeds out for you guys and I give you activities, I don't just like to put it in the trash. It's a living thing. And I personally don't like to destroy any kind of life whatsoever. But sometimes we have to do it. Okay? So that's kind of like my perspective. Very much like an ecocentric kind of perspective. I respect all life, whether it's a seed, whether it's a cockroach or whatever. I still sometimes I don't like to step on a bug like that, you know. But you have to do it. So that's one perspective that some people have. So we had some seeds here growing. in this plate, and if we took them from germinating seeds like this here, they would look like this. I want to encourage all of you to go home over this break, and you don't have to really sit around and watch this assignment anymore. But you put some seeds to germinate like this, and then you get them growing, and you set a camera to take a photo every 3 hours. By the end of the break, you would have maybe about 100 pictures, and you can put them together, and you would get a time-lapse video of your seeds growing. Okay? Now, right there, you're going to have some very modern kind of data that could eventually be used for a different style of investigation, a modern-day style of investigation, where you're using technology to find out the growth rate of something under certain conditions. And you don't have to be going with a ruler or anything like that, because if you put a ruler in your video, you'll get a sense of scale also. And you could get some very powerful evidence. This population inside of this plate right here, I'm calling it a population, Fuad, because you see a population, right? It's a group of things of the same kind living in a specific area. So we talk about the population of planet Earth. About how much is it, 8 billion? About 8 billion people. We can talk about the population of Abu Dhabi. We can talk about the population of the UAE. We can talk about how many oryx we have living in the desert of Abu Dhabi. That's all of those are populations. And we can talk about how many mung beans are growing in here. We can literally count it. But if I wanted to count how many snails are living in a garden that is the size of this campus, would I hire 100 people to go count every snail? Or would I come up with a different strategy? I'll hire 100 people and say, go count all the snails for me. But you think that's how scientists do it? They can't hire 100 people, so they have a few people working. It might just be them, and they want to find out how many snails are living. If this were a big forest then, the size of this campus, and there were snails living on every one of these plants, we would have to use a technique to estimate the snail population. So what we'll do is, and here's how it works, and then I'm giving you guys a chance to do the activity. We'll go out and capture some snails. You guys know how to capture a snail? Yes, you pick it up, right? A snail is not going to bite you, right? How many of you watch SpongeBob? What's the snail? Yeah. Gary is a snail. Gary is a famous character in SpongeBob. That's SpongeBob's pet, right? Yeah. Yes. My son is a little bit older than you guys, and he used to watch SpongeBob a lot, so maybe the same for you guys. Anyway, so you go out and you capture some snails, and you put a mark on them. Ben, but when you put this mark on the snail, you want to ensure that the paint that you put on the snail is not toxic, and neither is it permanent. You don't want it to be like some permanent yellow fluorescent that the predator would quickly see the snail and eat it. So you want it to be a non-toxic, non-conspicuous type of paint that you put on the snail. And then you release it.
Can you use tape?
You can use tape, yes. You can use some kind of tag. Then you release the snails and you allow them to mix in their population. When they mix in their population, you come back and you take another sample sometime later. And then there's a formula that's on the video that I've put on Google Classroom that I want you guys to watch. I want you to watch the video, and then I'm going to give you and a partner next to you. So we've got 1, 2, 3, 4, 5. We've got about 10 groups we're going to create. If you want to be by yourself, I can get you some beans for yourself. The beans are going to represent snails. Okay? Because we don't really have snails. We're going to make a model to what I shared on the video I just mentioned here in my live discussion. We're going to go watch that video, and then we are going to discuss with our partner how we will make a model to test what's called the mark, release, recapture method using the Lincoln Index. This activity, all activities that I share between now and the summative are going to be included on the test, plus the entire work packet. So I've done it like that so that you guys would not be stressed about what to study. The work packet, you do that, and all these activities, you do them. So let's go on Google Classroom right now, watch the video, and then I give you and a partner, or if you want to be by yourself, a cup with some beans and a piece of paper, and I want you to test how good the Lincoln Index is, and I'm going to come around to find out how it's going for you.